So good day. We'll be discussing genetic algorithms on behalf of Group 2. So we begin by citing John von Neumann's vision of machines that somehow mimic the behavior of natural evolution. He pondered the possibility of computer programs that could replicate themselves automatically within a self-correcting and thus self-improving framework. These improvements align with the concept of mutations and evolution and are ultimately headed towards finding the best version of that specific program that solves a specific problem. Additionally, von Neumann sought to address further critiques concerning his preconceived theory. Unfortunately, he was unable to explore this theory even further due to his death. We then move on to the development of evolutionary computation as it's now known today. So after his death, the concept didn't fade away, and in the early 1960s, several research groups began experimenting with what is now known as evolutionary computation. Among the most notable contributors to this field was John Holland from the University of Michigan, who is considered as von Neumann's academic descendant. Holland was further enlightened by Darwinian evolution and Fisher's work on natural selection, and thus pioneered genetic algorithms. He viewed these algorithms through the lens of computer scientists thinking about programming in terms of breeding strategies used in agriculture and animal husbandry. His work led to the development of a formal structure for these algorithms and broader applications in adaptation within both natural and artificial systems. We then move on to the influence and legacy. So subsequently, John Holland's 1975 book called Adaptation in Natural and Artificial Systems laid down the theoretical foundation for genetic algorithms and adaptive systems, which influenced many other individuals, one of which includes the author of the book of reference, which is Complexity by Melanie Mitchell.
Now we move on to how genetic algorithms actually work. And in a nutshell, they work by mimicking natural evolution. We start with an initial population of solutions. These solutions are usually not very good, but they only need to serve as an initial starting point. Usually, they're even randomly generated. The important part here, though, is that these solutions should be represented in a form that has a set of parameters that can be altered. This list of parameters per solution can be considered as that solution's chromosomes. We then iterate using these solutions, with each iteration being termed as a generation like real-life generations. With each generation of solutions, the fitness level of each solution is assessed. The fitness level is basically how well the solution actually works for the given problem. The most fit individuals from a current generation are selected for breeding. So our solution's chromosomes can be crossbred here, where portions of two solutions' chromosomes are combined to create their offsprings. They can also have mutations applied, where parts of their genome are randomly changed. Doing this enough times eventually gives us a pool of candidate solutions that we can treat as our next generation. And then we can assess that generation and repeat this process ad nauseam. So the most fit individuals from a current generation are selected for breeding. Our solution's chromosomes can be crossbred here, where portions of two solutions' chromosomes are combined to create their offsprings. They can also have mutations applied, where part of their genomes are randomly changed. Doing this enough times eventually gives us another pool of candidates, which we can then repeat the process for until we are satisfied. Uh, this usually takes place until a specific condition is reached. It could be until one of the solutions becomes good enough or until a max number of iterations is reached, or even if the solutions are no longer getting better even after each generation. So to cover an example of how a genetic algorithm can look like, we can look at this sample situation. Let's say that we wish to program a robot that cleans the floor for us. The code for moving, cleaning, and all those other bits is already done, but all we need to do now is to code into it the best and most optimal way for cleaning the room. We can do it, of course, manually, but the point of genetic algorithms is to hand off the problem of figuring out the solution to the computer. And also, this is a simplified problem, so the idea of genetic algorithms doing the work for us only gets more enticing as you actually deal with more complex situations. Abstracting it, we can say that the room can be divided into a 10 by 10 grid. Wait long. Wait. So let's cover an example of how this genetic algorithm concept can be applied. So let's say that we wish to program a robot that cleans the floor for us. The code for moving and cleaning is already done, but we need to program into it a way so that it can find the best and most optimal path for cleaning the room. Now, we can do that manually, but the point of genetic algorithms is to hand off the problem of figuring out the solution to the computer. And also, this is a simplified problem, so the idea of genetic algorithms doing the work for us only gets more enticing as you actually deal with more complex situations. So, for example, let's say that a room can be divided into a 10 by 10 grid, with trash littered randomly in each square. The first thing we need to do is to try and define the solution in a way that can be represented as a chromosome. The solution here would be a way of telling our robot what to do to traverse the room. So for example, we can define an action for every situation it could possibly be in. The robot can see the tile to the left, to the right, in front, and behind it, alongside what tile it's currently on. And then each tile can either be a wall, an empty space, or can have trash. Depending on this, we can then say that the robot can respond by going any of the four directions, up, down, left, right, staying in place, picking up the trash, or going in a random direction. Using combinatorics, we can say that there are at most 243 different possible situations. There's 5 tiles, and with each tile having 3 possible states. Each situation can then be greeted by the robot with a specific action. That list of actions it will do per situation is our solution or our chromosome. And since we've defined it this way, we can actually, to get our initial population, it's as simple as generating those strings of numbers randomly multiple times. Next, we calculate the fitness. We simulate the robot and the room with the robot enacting our chosen solutions. Since they're randomly generated, they're not going to be good right now, but some are going to be better than others, and that's all we care about right now. The important thing here really is defining our fitness function, a way that we can say that a solution is good. One way we can do this is to assign point scores. If the robot picks up trash, then it gets plus points. If it crashes into a wall or tries to pick up trash where there is none, it gets negative points. Combined with a maximum number of moves possible, then we have all the facts needed for an optimization problem. Given a limited number of moves, what is the best way for the robot to move across the room that nets it the most number of points? For even more granularity, you can even weight the points so that, oh, you really want a robot that doesn't crash into walls, increase the penalty points for it. With the solutions and the fitness function in mind, we already have most of the tools required to run the genetic algorithm. All that's left is to iterate. The most fit solutions from the generation are crossbred, with a new child solution being formed from parts of parent A and parent B. You can also mutate the solution at this point, changing small parts of it randomly. And then we repeat the process until we have a new population. And then we repeat the entire process again of calculating fitness and iterating repeatedly until we get a solution that has the highest fitness or until our max iteration count is reached. And it's as simple as that. Given enough generations, and if we set the algorithm correctly, it will eventually give us an algorithm that performs the best under the given parameters, all without having to tell it how to actually clean the room.
So the use of genetic algorithms in our world involves a wide range of fields, including machine learning, telecommunications, data science, and more. For our presentation, we shall consider its application in the context of airline systems, specifically regarding scheduling, crew employee rostering, passenger travel itinerary optimization, and airline network design. So in terms of flight scheduling optimization, genetic algorithms can be used to create optimal schedules for flights, which take into account factors such as aircraft availability, crew scheduling, and passenger demand. The algorithm can explore different combinations of flight times, connections, and aircraft assignments to find the schedule that minimizes costs, maximizes revenue, and which helps them achieve better resource utilization, reduce delays, and improve overall efficiency. When it comes to crew rostering, we note how airline crews, including pilots and flight attendants, need to be scheduled in a way that meets regulatory requirements, minimizes costs, and ensures crew well-being. Subsequently, genetic algorithms can be employed to generate optimal crew rosters by considering factors such as crew availability, work rules, and personal preferences. This leads to more efficient crew utilization, reduced overtime costs, and improved employee satisfaction. The third example we will be discussing would be aircraft routing and assignment optimization. So allocating and routing aircraft efficiently is crucial for airlines to maximize asset utilization and minimize operational costs. Genetic algorithms can be used to determine the optimal assignment of aircraft to specific routes, considering factors such as aircraft capabilities, fuel efficiency, and maintenance schedules, among others. This optimization can actually help our airlines reduce fuel consumption, minimize the number of aircraft required, and improve on-time performance. When it comes to itinerary optimization of passengers, airline passengers often have complex travel itineraries, including multiple flight connections and class of service. So when it comes to the algorithms that are to be used, they can be applied to optimize their itineraries that reduces them into what is only essential, such as ticket prices, travel time, and passenger preferences. All of these will eventually boil down into having more attractive and cost-effective travel options, which leads to increased customer satisfaction and revenue. When it comes to airline network design optimization, we note how genetic algorithms can also be used to optimize the overall airline network design, including route selection, frequencies, and locations. So when we explore these different network configurations, the algorithm can actually help airlines identify the best network that maximizes profitability, meets passenger demands and needs, and aligns with the airline company's strategic objectives. So all in all, we can see how genetic algorithms are indeed useful in our world today, and we note how they are constantly evolving when it comes to their operations.